This is the tutorial for a tour of the RISC-V formal specification. My name is Rishiyur Nikhil, and in the foundation, as you might know, we have various technical groups that are chartered with specific goals, and one of them was a group founded about 2 years ago at this point called the ISA Formal Spec specification group, and so I chaired that group, and what you're seeing is the outcome of that. I'll have a little more about status and plans and all that little at the end of the talk. This is the first time I'm trying out these slides, so I hope they work well. And I'd like to give a thanks to a bunch of folks here who you see on the named on the slide, who helped give me some feedback on the slides, etc. And one of them is Prashant Munkur. You could raise your hand. He's from SRI, and he's actually the principal author of the spec that you're about to see. He wrote most of it, and he's the expert on it. So if you have more questions and stuff, he's another person you can ask. And if I make any errors or things because it's the first time through on these slides, I'm responsible, and maybe Prashant can correct me if I do anything wrong on that. Okay, so I want to just see a quick show of hands. This information that you see on the slide, you see a GitHub repository called the tutorial tour, and it has 2 PDFs in it. Slides tutorial.pdf, which is the PDF we're looking at right now. And there's another one called slides install.pdf that says if you want to build an executable version of the spec, etc., it has more details on how to do that. I tried to publicize this information quite heavily over the last 2 weeks, sending it out to various RISC-V mailing lists and all that. Could I get a sense of how many people actually saw those emails? Okay, not too many. And some subset of those, maybe you've actually been able to install and things. So you don't need to install anything. You can just watch the slides. The tutorial will work, but you might want to at least download the PDF because the screen is a little dim, and at the back, I'm not sure how readable they'll all be. The other thing is, if you want to do the execution, I'm going to be demoing the execution on my laptop, but you're welcome to follow along as well. Okay, so objectives. So the word formal is very scary to lots of people, and this tutorial is aimed to try to alleviate that, if in case some of us have those reactions. In the past, formal specs have been done a lot by very specialist people, PhDs, highly trained in this stuff. They do this on a daily basis, etc., and ignored by everybody else. Our objective really is to make this spec accessible to everybody. Anyone who wants to do anything with RISC-V, you're writing a CPU design, you're writing a compiler, in the same way that you would reach for the textual specs of the privileged and unprivileged art, you should be able to also look at these specs, maybe even only look at these specs if you're trying to clarify in your head what is the encoding of an instruction, what does it do, etc. So really the objective in this tutorial is widespread exposure to and familiarity with and comfort with the spec. So it's not aimed at professional formal verification or formal methods people. So secondly, so much of the tutorial is going to be just a reading spec. I'm going to show you fragments of the spec, the actual code. I'm going to explain it, so you're going to be learning the notation that is used by which we write the specs, etc. So most of it is just the first objective, which is reading. The second thing is the most common use likely to be made of this spec, apart from reading it, is as a reference against which to compare some implementation. And when I say implementation, it could be software, it could be hardware. You could be writing an instruction set simulator. You could be writing a compiler that's generating RISC-V code. You could be designing a CPU in Verilog. In each of these cases, you're trying to understand what exactly is the coding for this instruction, what is it supposed to do. And when you make your implementation, whether it's a simulator or a Verilog simulation or something like that, you might run some RISC code on it, and you want to know, did it do the right thing? So you could also run that RISC code on this formal spec and compare the formal specs behavior with your implementation and get a sense of whether your implementation behaved correctly on that program or not. That's likely to be the largest use of the spec in terms of executability, not formal methods, actually just as a reference simulator. So that's the secondary objective. The third objective is, as you know, the spec, RISC-V spec is a moving target. There's at least 6 or 7 other technical groups who are looking at vector extensions, bit manipulation instructions, just-in-time compilation instructions, things like that. And the spec, as it stands right now, covers only RV32GC and RV64GC. So over time, we have to add those. So it'll be good for a wider audience to be familiar with what does it take to add an extension to the spec. So that's basically the prelude to this as to whom I'm aiming this at. So if I can say it in a slightly lighter vein, dear reader, it may be previously have seemed abnormal to consider using an ISA spec formal. But our future RISC-V tasks loom large and can terrify. As CPUs, compilers, and IPs, we design and verify. Greek symbol-laden formal specs may make us queasy, but this one's different. It's really quite easy. Instead of passing out in shock, wheeled away in a gurney, this tutorial, we hope, for you, starts a more pleasant journey. And to borrow a political idiom, you can all chant if you like, ISA, ISA, ISA. Okay, so some credits. As I said, Prashant is actually the principal author of the spec, but you can see some other names also on that first set of names who have contributed to the spec. My name is there in a cameo role. I just did the F&D extensions within the last 2 months. I did part of it, and Prashant did the other part of it. So those are the people who wrote the spec. So just to clarify, SAIL itself is a language that is meant to write ISA specs in. That is not a RISC-V specific thing. You could write ISA specs for other architectures, and I'll have more to say about that later. RISC-V is just one ISA which has been coded in this language called SAIL. So the SAIL general purpose language, that's the second paragraph in my slide. The chief reference is a paper in POPL this January, which is cited over there, and you can see the list of authors there. Those are the people who are the principal authors of the overall SAIL language and the SAIL implementation and so on. And Peter Sewell, the last name you see on that list, is a professor at University of Cambridge in the UK. It's his research group that is sort of at the center of this activity, and he's the leader of this effort. And finally, I'd like to thank also the members of the technical group. We've been meeting almost on a weekly basis for almost 2 years now. Actually, we were pursuing 6 separate approaches to writing the formal spec. So a lot of back and forth discussion, and then within the last 6 months, general consensus that let's center on SAIL as the canonical spec for the foundation. Doesn't mean the other versions will go away, but because everybody is doing it not just for the foundation, they're doing it for their own research goals, et cetera. So actually, there are several efforts underway. SAIL is just one of the outcomes of this. Okay, so here's an outline of what I'm going to talk about. After a little introduction, we're going to dive into the reading part of the tutorial. I'm going to talk about registers, instruction fields, exceptions, all kinds of things like that. Then that will be most of it, I think. And then we'll talk about how to execute it. And I'll specifically show examples of executing it on the so-called standard RISC-V ISA tests. And I will also show how they're executed with the official compliance tests that are under development within the compliance working group of the foundation. And then at the end, the one thing that I would like to get to if we have time is the adding of new extensions, because I think that's a lot of new extensions are coming up soon. And then we'll talk a little bit about concurrency. Actually, concurrency is necessary for any modern ISA to talk about concurrency. For this tutorial, we're going to completely ignore concurrency, but I'll have a few remarks to say about it at the end. And in particular, concurrency interacts with the other part of the formal spec of RISC-V, which is the weak memory model. So you can think of the overall formal spec of RISC-V as the instruction set semantics, encoding and meaning of instructions. And then there's a weak memory model semantics, how do memory systems behave? And these, of course, interact through load stores, fences, atomic memory ops, and things like that. So there was a separate technical group that did the memory model, actually also using SAIL for a couple of things. And I'll say a little bit at the end about that. Okay, so let's talk about a little bit about an introduction. So what is an ISA formal spec? In some sense, it's just another program. You're writing a program in some particular language that is trying to express what the ISA says, which of course brings up the question, why not do it in an existing programming language like C or C++ or something like that? Each of those is also a formal spec. You know, Spike is a formal spec in that sense of the ISA. So is the Open MVP Sim from Impetus, for example, and whatever's in QEMU, etc. The issue is that we are also trying to be, the key objective here is communication between me and you. If I want to explain what an instruction says to you, how do I do it? That is not something people typically reach for C code or C++ code for. Or you're trying to write it in a concise, very clear, precise manner. So having a language that encourages that kind of style is very important. The second thing is we do want it to be executable because for the mention I said earlier about being able to talk about reference models and golden reference models and so on. And a very high priority for us is readability by the casual reader. So this is fairly new for instruction sets. Actually, if you look at the landscape of formal specs for ISAs, except for RISC-V and ARM v8, there isn't anything out there, research or commercial, that's a kind of a full-blown, full ISA formal specification. ARM is probably the first who took this seriously and several years ago started this, and they developed their own internal proprietary formal spec language for describing the ARM ISA, and they have the entire ARM v8 spec described in that language. SAIL is the next one down the pike in terms of being there, available to people. The ARM spec is internal. I'm not sure there's great access to it or the tools that go around it, etc. But interestingly enough, ARM is located in Cambridge. The SAIL group is located in Cambridge in UK, and there's been a lot of collaboration between them. And in fact, the SAIL group has with agreement with ARM, taken the internal formal spec in ARM and automatically translated into SAIL. They've been able to execute that SAIL code, boot Linux, etc., and run it through the many tens of millions of verification tests that ARM has to make sure that the spec is doing the right thing and it's agreement with their own formal spec. So it's interesting that RISC-V is the first ISA where the formal spec is going to be easily and widely available to all of you and researchers who want to do interesting stuff with it, or more interesting things with it. And this has been a high priority in both the design of the SAIL language as well as the spec of RISC-V in that language, so that it be easily accessible to people. And the last thing is, for any formal spec, you also want to be able to connect it to various formal tools. You may have your SAT solvers and your theorem provers and your proof assistants and things like that. So you want to be able to parse the spec, characterize what the semantics are, and feed it into other tools people might be writing for these kinds of things. And this is why many of these things are not covered by traditional programming languages, and that's why we're writing it in this particular language called SAIL. I think I will skip this since this is mostly repeating what I just said. It's various uses. Let's just talk about a few of the last few bullets about how you can actually then use the formal spec other than as a golden reference model during execution. You can use the semantics, for example, to write instructions that generate tests automatically. You can use the formal spec to write analyzers that can check coverage of instructions. The biggest an interesting holy grail would be correct by construction or formal proofs of correctness of actual implementations. So if I were to give you a design written in system Verilog, and I were able to somehow characterize to you what are the semantics of system Verilog, here you have the design, the spec written in SAIL, and we can characterize the semantics of the SAIL language. If you can relate these two to show that, in fact, your system Verilog correctly executes RISC-V instructions, that would be a wonderful thing. That would be a huge help in your verification effort. So that's an example of a CPU implementation. But another example on the other side of the hardware-software barrier is if I give you the semantics of C somehow, and I give you a C program, and say the C program does something, it sorts an array, for example, we compile it through a compiler and we produce the RISC-V binary, which is the ISA basically. Can you show that it correctly does what the C program says it's supposed to do? And even better, can you use these semantics to, given the semantics of C and the RISC-V ISA, to show that for any C program, the compilation will be correct. So you have to relate the semantics of the source and target for that. So this is another big use of this. But much of what the last few things I said is still early research stages. It can't be used in anger yet. Okay, so let's move on. So this is again repeating. You can, at a minimum, you might want to just download the slide deck itself and follow me along. I don't know how bright the projector is and readable at the back. But you could do that. But the other thing I would recommend is there's another slide deck called installation there. The first part, again, I recommend just to read the spec. You can read because it has all the source code in it. The second part of the installation, which is a little more involved, is how you install the implementation of SAIL so that you can compile the spec into an executable and run binaries and things like that. I'll demo all of this anyway. I mean, not the downloading part, demo the things, artifacts that come out of that. But if you do it yourself, your experience will be that much richer. Okay, so let's jump into reading the ISA spec. So just in terms of navigation, you can see on the top of the slide on the left are the sections of my talk, and for each section on the right, you'll see the subsection that we're talking about. Okay, so SAIL is a DSL, domain-specific language, and all that means is it's a language purpose-built for expressing some kinds of this, specific kinds of thing, in this case, ISAs. And you see a list of ISAs that it's been used for, all of ARM v8, all of RISC-V towards the currently ratified spec, basically. Also all of MIPS and parts of x86 and IBM Power as well. For MIPS particularly, and also for RISC-V, given there are other groups in Cambridge who are doing extensions of MIPS and extensions of RISC-V for security, there's lots of stuff even on extended versions of this ISA. So the main SAIL manual, I have a link up there. It's not very comprehensive or complete. I think for this tutorial, you don't need to read that at all. Everything we're going to learn the notation of SAIL as we go along by reading the RISC-V spec. And I think that should be adequate at least for a reading literacy. If you're going to be adding extensions and stuff, then you might need to go into the SAIL manual itself. Okay. So at the bottom, so you see two links there. One link is for SAIL in general, common for all the different ISAs, the SAIL language itself and its implementation. And the second one is specifically for the RISC-V spec written in SAIL. Okay, so I'm going to go through a lot of nitty-gritty detail, but before that, let me just give you a quick flavor of this by showing you the execute semantics of one class of instructions. So as you will see in this example also, all the excerpts I have, on the top of the box, it tells you which file it came from. So you're welcome to look at it. And if you've already downloaded the repository, or if you're reading these slides later on at home, you should by that time download the repository. And I would recommend that wherever you see one of these displays like this on the slides, go and look at the actual file in your text editor, because it has a lot more context, and I've elided a few things here, et cetera. You'll see the full detail over there. Okay, so this, what this is saying, let's see what this is saying. So first of all, over here, you see the name of a function we are defining called execute. Okay, so we're talking about the execution semantics. Over here, we're seeing what is the argument. It's a single argument for the execute function. And the notation is as follows. You can think of, first of all, as R-type. What's R-type referring to? Well, if you look at, let's take a look at this. So here's a page from the unprivileged spec, textual spec. And at the top of the page, you can see of each of these pages, you'll see a reminder of what are the instruction formats in which all the different instructions are fitted into that format. So at the top, you'll see the R-type. That's the register-to-register class of instructions. And so the R-type in the sales spec is referring exactly to that. And in the R-type, as you will see here, there is an opcode, which is what we think of as a major opcode, a func3, which is a sub-opcode, then register designators, et cetera. So, whoops, went the wrong direction. So this is basically, you think of this as an abstract syntax tree for the instruction. You can also think of it as a decoded view. That is, you've gone through the question of how it's all put into 32 bits, and you're just abstractly saying, oh, it's an R-type instruction, and here are the fields for it. After this, the equal sign is the body of the function, which is a block enclosed by these braces. And actually, yeah, let's move on here. So the first two lines are doing kind of the obvious thing. They're reading X, capital X here refers to the register file. So it's reading the register file indexed by RS1 and RS2 to get the two values. Then in this line, we are saying we're going to define something called the result. Its type is going to be xlen bits, which you'll see in a moment, means bit vectors of width xlen. And finally, the right-hand side says, I'm going to do a match on what the op is. And the op conceptually is based on those func3 and func7 fields, which is the detailed opcode that we're interested in. So you see it's just a big branch or a case or a switch statement, if you're familiar with all of those terms. The left-hand side matches the op, and depending on what the op is, we do the appropriate thing on the right-hand side. And here, we're just adding the two values. Here, we are shifting the value, RS1 value, by a certain amount, and the amount is picked up depending on what our current setting for xlen is, either 5 bits or 6 bits. And then finally, we're assigning that result into a register. And then finally, we retire success. Again, I'll say more about success and failure in a moment. But that's it. That's the full execution semantics given for at least those two particular opcodes. Now, if you go to the repository, the sale RISC-V repository, and you go into this particular directory called model, the entire model is set there in a bunch of files. And that looks quite intimidating the first time you look at it, because there's lots and lots of files there. And what I'm hoping is that this tutorial will give you a starting point so you know how to navigate through all of these things. And then we're certainly not going to go through all of these today. We're going to go through a few excerpts of a few of them. But once you start understanding the structure, it should be easy to start following it. So the key particular files I want to draw your attention to are, you'll see a bunch of things called RISC-V instructions, axt.sale, for example. That A is the A or atomic memory ops extension for RISC-V. Similarly, base is the I, the RV32I, RV64I base. C extension is for the C or compressed instructions. M extension is for the integer multiply divide extension. So it's organized according to extension in that kind of, in a modular way. And you can, when you build, you can use whichever ones are needed for the particular kind of configuration that you might want to be building with or without those different extensions. We're going to see more details of instructions in those files in a moment. You'll also see stuff on virtual memory. You'll find things here on registers and so on. So we'll go through all of those. Okay, the other point I should say is SAIL does not have a, given its intended purpose that it's just for defining ISAs, it's not meant for sort of general purpose programming with the large or anything like that. So it doesn't have a package or a module structure. So in many languages, you have packages and modules which are about namespace management. You have import clauses and export clauses. There's none of that in SAIL. Conceptually, a SAIL program is just a concatenation of all of these into one big text. And we'll concatenate it depending on which extensions we actually want. Okay, then finally in the introduction, just a little bit about type checking and strong types. So SAIL is a strongly typed language, and it is a statically typed language. In other words, strongly typed means it has a very rich notion of types, and statically typed means it has to pass type checking in the compiler before it even accepts it as a specification, let alone generating code for an executable out of it. Many of the types you'll see are very familiar from any programming language: structs, unions, vectors, things like that. Perhaps the most unusual part is really about bit vector sizes. So in a programming language like C, you basically have 4 sizes for scalars: uint, 8, 16, 32, and 64, and then you build structs and unions and vectors out of those things. And if you wanted a 23-bit value, you'd pick an integer that's large enough to hold it, and you'd ignore the upper bits, for example. In ISAs, that kind of view is kind of deadly. You want to exactly represent bit widths, and you want to exactly check that the bit widths are correct. You want to take care of things like overflows and underflows on those bit widths. You want to, and these bit widths are often related. So this is all strongly encoded in the type system of SAIL, so that there's a very strong guarantee that if you just got through type checking, that you got all the widths exactly correct, and there's no silent extension or truncation going out that may show up as a bug sometime later. Okay. The other thing is also keeps track of effects, like does this function read a register? Does this function write a register? Does it talk to memory, etc.? We'll talk a little bit more about that later. So let's get started on actually reading the actual code. So here are 2 files called RISC-V xlen32.sail and xlen64.sail. And they're basically defining the xlen that within which we're going to we're going to assemble a spec, and from which we can also build a simulator for that. A small point I should make here is that if you read the textual written specs, you'll actually find that it is possible, although I know of no implementation that does this, it is possible for an implementation to simultaneously handle RB32 and RB64. There are actually fields in the M status register and things which are writable fields where you can change the so-called xlen encoding. So it's entirely feasible, for example, that you might have a kernel or a supervisor running in RB64 mode, and it runs a user-level application program that's in RB32 mode, and that can be switching dynamically as you go in and out between those levels. The SAIL spec doesn't do that yet. Right now, it is statically configured for either RB32 or RB64, and depending on which we want to do, we would include one of these files in the build for that. It is possible to do what I just said, but that's future work. Okay, so getting into syntax again, the type keyword that you see on the left is introducing a new type to the system, a new type declaration. And when you say xlen:'int, you're basically saying that xlen, this type, new type xlen that I'm bringing in, is in the class of things that are integer types, numeric types. In other words, as I said before, when we're talking about widths, we're going to, at the type checker level, do some arithmetic. So for example, if you have a function that concatenates a 5-bit vector with a 6-bit vector, you want to express the idea that the output is an 11-bit vector, and your type checker should check that. So you have what we call a kind of types, which are int types, and so that's what the :int is saying. I'm defining a new type of kind int, and its value is the same as the type 32. Xlen bytes, and then Xlen bits is saying bits Xlen. So bits is the type of vectors, and rather than having unspecified size vectors, the parameter to that type, bits, is another type. You could either have written 32 there directly, or you could have written Xlen to say that this is a vector that is exactly, bit vector that is exactly 32 bits wide. Okay. Now let's talk about values in the integer registers. So we've already defined here Xlen bits actually, which is good enough. It's bits Xlen. It's a bit vector of size Xlen. But in various functions, etc., it might be more convenient to use a more readable name for what bits are these. And so this is just a convenience, reg type. And then what we're doing in the next line is we're defining a value. We're introducing and giving and binding it to a value, and name for it called 0reg, which is the value of 0 registers. So first point about the clauses you're seeing, when you see the type keyword up front, you're introducing a new type. You're declaring a new type. When you see let, you're introducing a new value and initializing it to what its initial value is. So here it's saying we have a new name called 0reg, and it's conceptually the register that is always going to return 0. You won't be able to write to it, and but you'll be able to read from it. And the value that you are doing here is shown on this expression. So in Sail, when you write a hex constant, a literal constant like OX0, the width is taken as whatever is implied by what you wrote in the literal. So in this case, OXO will be a 4-bit, it'll be a bits 4 type. And then the XZ is just using a predefined function in Sail to 0 extend that to the appropriate width. So this is where the type checking and type inference in Sail is how the compiler knows how much it should extend it to. So you might think that normally extension would also need another parameter which says how much should I extend it by, or to what width. That's implicit in the type already from that, because we know that this is a reg type. It must be Xlen bits, so the type checker will know that the extension Z in this case must go from 4 up to Xlen bits. Okay. Now let's talk about registers. So what we talked about in that slide was just about values in registers. Now we're going to talk about registers themselves. And this is introduced by the keyword on the left, which says register. So that's, as you might imagine, in a language intended for ISs, you would have some way of declaring registers, and that's what the register says. So the first line, for example, says that we're introducing a new name called PC for a register, and it's going to be a register, and the contents of that register is going to be Xlen bits. So that's telling you how wide the register is. And in fact, on the right, it doesn't have to be bits 32. It could be any type you like. So it's all strongly typed, and Sail will manage all the types for you there. Similarly, X1 through X31 are defined as registers. We don't declare any X0 because, as you will see in a second, X0 is defined as the constant 0 register in RISC-V. So we'll take care of that in the read and write functions rather than actually creating a register for it. I should also remind people that anytime something is not clear or you have a question, please raise your hand, and I'll be happy to take questions at any time. Okay, so here's a function now for reading from the register, reading from the register file. So the register file is in some sense implicit in the fact that there's no entity called a register file. You could do that in Sail as well, but in the code as written, it's just 31 separate declarations for registers. And in this reading function, we are going to read it. So now comes the first part of a little bit more tricky notation, so we'll spend a little time on this. So the first thing to focus on is just the part where I'm wiggling my cursor right now, the regno tick n arrow xlen bits, right? That is the input-output type of the function. The thing on the left of the arrow is the type of the argument, and the thing on the right of the arrow is the result type that the function produces. So the argument type, regno of n, is basically asserting that the input argument must be an index, a register index, a register number, and in particular of n. And further, this notation up front is further constraining what n can be. N must be any value you like between 0 and from 0 to 31 inclusive, or 32 exclusive, whichever way you read it. So this is a constraint on n. This says this must be a register index that conforms to n. That'll be the argument of the function, and in the actually text of the function, this argument r will have this type regno of n. And then the thing on the right is the result type coming out of the function. It's xlen bit. So what you read out of the register is a bit vector of size 32. And then the final part here you're seeing is an effects declaration for this function. So if you write a function in C called foo and you're calling it from somewhere, from its type, you can't tell what foo is actually going to do with the argument. It could read or write a file, it could talk to the network, or it could just add 1 to it and return it. It could be a pure function. And you can't make out the difference either in syntax or in types in C or C++, for example. So Sail tracks what happens in these functions so that you can tell from the type whether it's a pure function or not. If it's an impure function, what kinds of things could it do? So these things are called effects. So in this particular case, we'll first just look at the first one. It's obviously going to read a register, so that's an obvious effect. I'll talk about escape in just a moment. So again, stepping back to this notation, val is introducing a name and giving a type declaration for it. So I'm going to what it's announcing to Sail is, or to the reader who's reading this code, is that that this name Rx is, I'm going to tell you what it is, but for now I'm going to tell you what the type is, and everything to the right of the colon is the type of that. So it's a type declaration of Rx. And then when you say function RXR, you're actually saying, okay, now I'm going to tell you what the function actually is. What does it do? So here's the same name Rx, and then R is the argument of the function. Okay, let me think okay. So now let's take a look at the body of the function. So once again, we have these braces, and in the braces we have two items, this let item and this final thing over here. So what you have in braces is a block. It's in some senses similar to C, but in Sail, every expression has a values. Blocks have values, etc. So in the value of a block is treated as the last item in the block. So you can give a series of things. Typically, the things before the last item are either bindings of values, or they might be just expressions you execute for side effect, and then the value of the last expression is what's returned as the value of the block. So let's look at that in a little more detail. This let binding is basically saying I'm introducing a new name called v, local, inside this function, just a temporary name for convenience. The colon reg type is telling you what type that value has. It's going to be an actual register, so it's not the contents of a register, it's an actual register that's going to contain a bit 32 thing. And the equals then goes to our right-hand side, and a match expression in Sail is like a case or a switch statement, but it's an expression. It also has a value. So what it's doing is it's matching R, which is the thing that came in as an argument, against each of these patterns on the left-hand side. And it goes through them sequentially, top to bottom, the way you've written them. And for whenever it matches a pattern, it returns the right-hand side as the result of the match expression. So what you can see here is if you match 0, you're going to get this special register that just reads as 0. And if you have any value from 1 to 31, you're going to return the appropriate x, x1, x2, etc. You're actually returning the register itself. Let's leave out this last line for a second. Essentially what V becomes is the register itself. And then this last function is something that reads the value out of the register. It's just a function defined somewhere else in the code that reads the register. Now, actually, we could have, it's just reading the value out of the register. Now, one of the things you'll see in the Sail code is because people are playing around with extensions and so on, there are lots of places where you'll see a little function that seems to be doing nothing. It's just, in this case, it's just returning the value out of the register. But that's a place where you can put in a hook that does something special. So for example, if you have a security extension or something, you might do taint tracking or something, you could put in all those things into these hooks. So the code does have a lot of, to first reading what might seem like an unnecessary function call sitting there, but it's in anticipation of the fact that we might want to put in a hook over there. Okay. Okay, I think I have said everything out here. And so I hope the general intent is clear. We're defining a function. The val line tells you that it's a type declaration for the function that we're about to talk about. And then the function line tells you what the function actually is. And in the function line, we're just doing a big pattern match on the register index to pick the right register, and then we're reading the register and returning it. So let me talk a little bit about the assert here and the escape clause out here. This escape is here because this assert is here. So what this is basically saying is if you gave me an index that was not in the range 0 to 31 inclusive, then it's an error. So here it's being expressed as an assertion which is going to fail, which will fail. And because this function can, instead of returning a value, it can fail, that effect is called an escape effect, and that's why the effect is there in the effect declaration. Now, probably many of you are wondering, how can it ever be a value that's not in the right range, given this constraint I have here on the type, which says that n must be between less than equal to 0, greater than equal to 0 and less than 32. That should happen. So basically, if you think of what the compiler or the type checker has to do, it needs to analyze this match statement and prove to itself, given the type declaration that you've given me, that I will not have an undefined match out there. So that part needs to be strengthened in the Sail compiler, but once you do that, you should be able to remove this line and also remove the escape clause. But right now, you might get an error message about incomplete specification of the match. Yeah. Yeah. That's a good question. Maybe let me repeat the question. The question is, can the compiler infer those effects? And I'm going to make a guess, and you can tell me whether I'm right or not. Which is, I think, so you don't have to always give declarations for things that you introduce. So you don't need. I don't think you need that val line up front, maybe. And if I just gave the function, then yes, it will infer it, and wherever you use it, check that you have it. But if you do give me a val line, you should tell me exactly what it is. And it will check that the effects in the function, the inferred effects, actually match what you claimed are the actual effects. Is that a correct? Yeah.
Why are REG an effect at all?
Sorry?
Why is REG an effect at all? The reg file from REG is pure, is it not?
Well, it depends.
Those other lines that are pure,
So it depends on what you want to do with the spec. So if you're just thinking of the pure spec, you're absolutely right. It's pure, so you in a certain sense, it's a trivial or a silly effect. But suppose I was writing a system where I was counting how many times you read that register or something, right? So you may be instrumenting or hooking things into it, or for security reasons, you're taint tracking or something like that. You may want to hook things into it that do other things than merely read the register. So this is in anticipation that this would be a useful effect to have. So for most cases, we probably don't even think of it as an effect. Yes?
Coming from functional programming, everything you said made perfect sense up until the point where you said that V will be the register, not the value of the register. Then you have to spool back and say, well, register type is now, it's an identifier for a register, it's not the value of the register. Is that right?
Yeah, so no, sorry, I'm not quite sure I understood what your question was. So just
Reasons for functional programming, you would expect that X1 evaluates to a value of X1.
no. X1 is bound to a register, right? So even in a conventional programming language like C, when you talk about X, it's actually a location. When you say X is of type uint8b for T, for example, it's a location which contains a value of type uint8t, right? And when you use it on the right-hand side of an assignment statement, you're actually doing two things. One is you're pointing at what the location is, and which is what we in semantics call an L value, and then you're reading out a value out of that, which is what we call an R value, right? So we're trying not to do that kind of punning over here. That is, when you just talk about a register, you're actually talking about the register, and then you apply an operation to it to actually read the value out of that. The other point I want to make regarding you mentioned functional programming. Actually, Sail is not a functional programming language. It's inspired a lot by OCaml and ML and functional programming languages. It is actually an imperative language. So you read these, you read these as statements which may have side effects on them, and things like X, for example. I didn't pass X in I didn't pass the register file as a parameter to this function. If you were to write in a pure functional language, explicitly using functions, you might think of the machine state or the register file itself as coming in as an argument to this function, but you don't see that here, right? It's kind of implicit in this. Even in a functional language like Haskell with monads, you might think of this as a monadic function where that register file is implicit in the monadic value that's being passed through that function. Sail is not playing any of those tricks. It's really a very traditional C or C++ like imperative language. There is a global variable called x1 or x2 or x3, and you're actually going to read that from those are what are being referred to wherever you see x1, x2, x3 here in this code. Somebody else had a question.
Not the best name, it should be an index of name with the register value for register.
I agree. There is a little confusion. That instead of using the word V, we should have called it VJ or V or something, meaning RJ or something, saying I'm actually referring to the jth register here, and then I'm reading out of the jth register. You're correct. Sorry? Well, a value that could be in a register. So the output type is x-length bits, which is a bit vector of length x-length. It's an assertion failure. So now we have to sort of lift into general Sail semantics. What does an assertion failure mean, et cetera. For reading the spec, we sort of elide. I mean, you either have to prove it never happens, or you have to explain to me what does an assertion failure do. And the answer here is that then you have to sort of look at the overall Sail semantics. I mean, even this language, Sail, has a semantics which one needs to know in order to use it for formal methods, et cetera. But I'm just relying on your intuition here that, first of all, that in some sense all bets are off when an assertion fails. So the spec is in some sense violated somewhere. But the other thing I was also going to say is that if we can do our exhaustive match check better in the Sail compiler on that match, then that assertion can go away and the effect can also go away. Well, it'll be caught in the type checker itself because of the constraint. Yeah. It's kind of a fault. So if you look at the larger language, I mean, Prashant can maybe go into this more detail later, but I mean, I would imagine that in any language that has failures like this, that any function potentially could have two different outcomes. One is some value or this, and the larger semantics would encode what that means. And that's what's going to be happening in this case. So it'll be, it's in some sense not a well-formed question to say what's the value of the function then. It's what's the outcome of executing this function is either it returns and it returns a value, or the system has a fault and there's some way of talking about assertions and faults. Okay, so where are we? We are now almost an hour. Okay, so let me just make sure I've checked everything I wanted to mention. Yes. Okay. Here's the corresponding write function. We're going really bottom up, so this is very nitty-gritty to start with, and we're really going to get into instructions very shortly, I promise you. This is the corresponding write function. General pattern of how you read it, similar to what you saw in the read function. Let's see what's different. So first of all, where I'm wagging my cursor right now, on the left of this arrow, that's the argument of the function. And this notation, parentheses, a comma b, close paren, is a two-tuple or a pair. It's a pair of things. And one of which is just like in the read, it's the register index. But the other thing is a bits 32 value, which is excellent bits, which is the value you're going to be writing to the register. The output type says unit. Unit is analogous to void in C++ or Verilog or something. It just says, it's kind of a placeholder type which says nothing of interest here. Technically, it's a singleton type that has one value, therefore it's completely uninteresting. You can't do anything with it other than pass it around. And its effects here, we have a wreg instead of a rreg for write reg. Otherwise, most of this looks the same, except the right-hand side where it's sort of directly writing the assignments. Again, there's a stylistic choice you can make here. We could have written exactly the same match as we had in the read to first pull out the register and then done the register write as a separate statement at the end. Or you could directly write the statements inline like we're doing out here. Okay. Now, the next thing I want to say is that we don't use these functions all over the place directly as written. Sail also has an overloading mechanism. And overloading in general in programming languages refers to the fact that you have a name that can conceptually refer to some typically finite set of possible instantiations, and which one you choose is determined by the context or the type in which you use it. So this overloading function is roughly saying that I'm going to define a name, capital X, and I'm going to overload the two functions we just defined, Rx and Wx, onto that name, so that whenever you see X parens R in an expression, it means apply the read function. And whenever you see X parens R equals V in an assignment, it means apply the write function. And from now on, that's what we will use whenever we're reading or writing a register. Okay, the next point I want to talk about is, in some sense, a very interesting aspect. Yeah, sorry, go ahead. Excuse me. Close this and mute it, if I can. Mute everything. Okay, thank you. Please. Sorry? So in the code that you'll see later on, whenever you see this notation in an expression, it says it's the same as applying Rx to R. Oh, because there are more overloadings. I've aligned it. If you look at the actual code, you'll see there are a few more things. I've tried to simplify it to just focus on the things I want to talk about here. Sorry, okay. Dot, dot, dot is my elision. It's not part of the code. There are other things there that I've taken out of this sample that I put on the slide. I just wanted to say that amongst the things we're overloading X for are Rx and Wx. And whenever you see this, it means apply Rx to R. And whenever you see this, it means apply Wx to R and V. Okay? Okay, so this next thing is one of the most interesting differences in SAIL compared to most programming languages. So just imagine you were writing an ISS in your favorite language, C, C++, Java, Python, whatever, right? You might have a decode function, right? And what the decode function takes is a 32-bit argument, and it produces a data structure that represents the decoded instruction. That data structure is typically, if you think in C++ object-oriented terms, it's one of a series of class definitions, one per opcode maybe, or in C terms, it's a union type, doesn't matter, right? So that function, conceptually, is a huge if-then-else that is looking at the different bit patterns that are in that 32-bit argument. And depending on what those patterns are, each of the right-hand sides of that if-then-else will be, say, okay, this is an add instruction, this is a BEQ instruction, this is a BNE instruction, et cetera. Right? So that's your decode function. Similarly, if you look at you might write another function for execute. It's going to take one of these decoded instructions. Again, it's going to be a big if-then-else. If it's an add instruction, do this. If it's a BEQ instruction, do that, et cetera, et cetera. So the code is organized by function, decode function and execute function. If you look at an ISA manual, that's not how it's organized. What you have typically is a page per opcode, or a few pages, and in the page it says, here's the bit encoding for this particular opcode. Here's the meaning of executing this. Here's the assembly syntax for this particular opcode. You turn the page, the next opcode is described in a similar way, and so on and so forth. Even the RISC-V ISA manual is written, roughly speaking, in that style. So SAIL is meant to directly support that style of writing things. So it's just think of it as latitude versus longitude. You're doing a different slice on the same functions that you might have written in your favorite language, except that you're grouping them according to opcode, rather than grouping them according to decode, execute, and so on and so forth. Okay, so what you will see in the directory, first of all, is this file called RISC-V insts begin.sail. So when we assemble the overall SAIL program, this precedes all the instruction definitions, and it's announcing to SAIL or to the reader who's reading this code that these are the things for which we are going to be giving you scattered definitions. All right? So the first thing is a scattered union AST. So AST is the abstract syntax tree. You can think of that as the decoded view of the instruction. And it's a union that it's going to have a variant for each different opcode, except it's going to be scattered. I'm not going to tell you what those variants are here. I'm going to tell you that later in the code. Similarly, encode, decode, encdec. The first line, val encdec, is saying, I'm going to define a mapping that shows the translation between ASTs and 32-bit values. That's the instruction representation. So you can think of that as the decode function if you're going from the right to the left, from 32 bits to AST, or you can think of it as an encode function. If you're a compiler writer, you might want to go in the opposite direction to produce a 32-bit value from the AST instead. So the next line says scattered mapping encdec. So first of all, mapping is like a function. It's like a shorthand for defining two functions that are the inverses of each other. So we're going to use the same name, encdec, which will be applied either way to either go from 32 bits to AST or vice versa. And then the scattered keyword again says, I'm not going to tell you what it is now. It'll follow later on in the code. The third line, similarly, is the assembly, which is from the AST, from an assembly language program, how do I get to the AST, or vice versa. Now, you might think that from assembly, you might want to first go to bit 32 and then go into the AST, but that could be an internal detail. You could either do it directly or you could internally structure it that way. But here in this spec, we're just writing it directly as an AST to string mapping going into registers. Yes?
So let's assume now you don't support constraints, but let's say you support constraints and now you have to switch between 16 and 32. How does the syntax kind of look like?
Yeah, so first of all, this is, I'm mainly focusing on just the 32-bit instructions here, but the compressed instructions, 16-bit, are also described in the spec. So you'd have to have more variants that talk about bit 32s to ASTs, et cetera. For each of those, you'd have a bit 16 to ASTs, AST to bit 16. Once you get to AST, you might forget about those details. You might, so you've gone to the abstract view, but instead of xlen bits, you'd have bit 16 or something as its type for that. Okay, and the final scattered thing we're going to do, which is actually the meat of the semantics, which is the execute function. We already saw example earlier in one of the earlier slides about that. So this is saying execute is a function that takes an AST as its argument, and its output is something called retired. Now, technically, nothing needs to be returned on this because there's no result. This is more about when we're executing programs, one of the things in the RISC-V spec is counting the number of retired instructions. There's an instret CSR, for example, that counts how many instructions are retired. And so that outer level engine that is dispatching and executing these things needs to know whether you succeeded or not and whether you should be counted or not. So that's all that is. Otherwise, you can think of it as a unit or void return type out there. And of course, it can have all kinds of effects because we're talking about the full execute function of every possible instruction. So essentially, your whole list of effects will show up in here. And then again, by saying scattered function execute, it says, I'm not going to tell you here what the execute is. This will follow later on in the code.
So the case that you write already, these are the keywords here, right? So the sale has also registers memory, right? Because it was designed.
Roughly speaking, you're correct in your intuition. It's just that sale, you can in a prelude, you can define lots of things on your own. So if you're defining an ISA which doesn't have this effect, you could define a sale program which doesn't have. So there's a pre-declaration of various effects. So again, if you go to that directory and look at all those sale files, you'll see some of the files called prelude and things like that. Many, even things like plus, which I used in the addition. What does plus mean, right? These kinds of things can be defined in the prelude itself. So sale itself has a very, very small set of primitives, and typically you customize it for your needs for an ISA in a prelude, and then you start using those in that. But whether you think of it as a built-in or a library function or predefined, at this level, it doesn't matter. Okay. Done. Okay, so this is just a reminder of what I showed. Actually, I showed you this thing here, page from the written spec, unprepared spec. It's just repeating that. So there's these 6 encoding types for instructions that you see out here, and a couple of observations to make out here. So first of all, if you haven't, I don't know if everybody's studied these yet in RISC-V, but if you haven't, basically, what this is showing is for any 32-bit instruction, the bottom 7 bits 0 to 6 on the far left here, represent something called what I refer to as a major opcode. It could be a single. There might be only one instruction with that opcode, but there could be several. And if there are more than one, these funct3 and funct7 fields typically give you that extra information about what opcode it really is. RS1, RS2, RD are your classical source and destination register designators. And then some of these things have immediate types. So in some cases, the immediate is very straightforward. Like in the I-type instruction, the immediate is the 12 bits at the top of the instruction. But if you look at the J type, for example, you see that the immediate is taken from 20 bits, from bit 12 to bit 31, but they're not taken as is. They're permuted in a particular way to form the immediate that the instruction actually uses. So the spec needs to take care of all of these things, but these mnemonics are reproduced in the SAIL code as well as R type, I type, S type, and so on. Okay, so yeah, so we're in this file RISC-V types.sail. We're defining just convenient names for more readable mnemonic names for bits vectors size 5, bit vectors size 12, and so on and so forth. And now we're going to jump into two specific instructions, the LUI, load upper immediate, and AUI PC, that is add upper AUI, add upper immediate to the PC, which is a way of loading in constants, either absolute constants or relative to the PC constants into a register. So these have the U type format, which is shown in the picture over there. And in the SAIL code, in RISC-V inst base.sail, you will see that we are now filling out our first clause of what is that AST type, right? Where in some other language, you might think of defining a union type and then immediately showing all the clauses. We're going to do that in a scattered way, incrementally, and we're adding that first clause. And this basically says is that one of the kinds of ASTs is a U-type AST. And when it's a U-type AST, it has these three fields in it, which are just positional fields. It's a 3-tuple containing a 20-bit value, register index, which is a 5-bit value, and a UOP, which is going to be tell us whether it's a LUI or an AUI PC. So this is just like an algebraic type or tagged union that you might see in functional programming languages, except we're just specifying one clause of it in this line here. And typically, when we look at tagged unions, algebraic types in functional languages, the way you branch on which kind it is usually done in a so-called pattern matching statement. You saw the match statement earlier. We'll see more of them as we go along. So first, let's talk about I said there are three kinds of things we're going to provide as scattered definitions: the encode, decode, the execute, and the assembly to string and back thing. So we're looking at the first one here, which is the encode, decode. So what we're doing here is that we're, first of all, defining a local mapping. So this is not a scattered mapping. It's just a local definition here, which basically says, looks at this so-called funct7 field. So going back to this picture here. No, it's not looking at the funct7 field. Sorry, it's looking at the opcode field itself, which is these lower order bits. These two instructions, it so happens are unique in the sense that they take an opcode for themselves. So what this is basically saying is that if you have this bit pattern, then the abstract view of that is a RISC-V LUI, and this is again defined elsewhere in the file. There's a kind of an enum type which says things can be in RISC-V LUI or RISC-V AUI PC. So just think of them as symbolic names, and this mapping is saying with this pattern it maps to this, and with this bit pattern maps to this, and vice versa. With this abstract name you can produce this bit pattern or vice versa. So once again, it's a mapping. That means it's also revealed by this two-headed arrow here between these two types. And then finally, here is in this line 6 and 7, you're seeing the clause of the encode decode. And what it's basically saying is that a U type with these three fields becomes, so these three fields, if you remember the types, this immediate was a bit vector of size 20, RD is a bit vector of size 5, it's a register index, And op is one of these abstract operations, uops, right? So what we're doing is we're taking the bit vectors as is, immediate and RD, concatenating them. So this little at is the sale operator for concatenating bits. But op is not a bit field, but by applying encode, decode, uop, we can get a 7-bit field out of that. So this whole expression here is a 7-bit field. And when you concatenate that all together, you get your 32-bit encoding of that. So basically, very declaratively in one line, using a lot of pattern matching and type constraints, et cetera, we're defining the mapping from the AST type. So we don't have to write a separate parser for or a decoder or anything. This is doing the decode function for you, essentially. This is the decode function for this kind of instruction. Okay, so and again, on the right-hand side, you see we have not made any declarations of how wide is immediate or how wide is RD, et cetera. All of this is constrained by the strong type checking, that immediate must be 20 bits, RD must be 5 bits, and encode, decode, uop must be 7 bits. Okay, so now we're going to get into the, once we've decoded, yes, right? Yeah, okay, that's a good question. So just to repeat the question, what he said is that sometimes the decoding is value dependent on what the value is in that. You'll see a lot of this in the compressed instruction set, for example. You'll see that in this particular field, which is RS1 field, if you have 0, it's actually this instruction, because for that instruction, we don't need an RS1. Whereas if you have a non-zero value, it means this other instruction. So in these mapping clauses, which are not shown in this example, you can actually put guard predicates on either side of these things. And those guard predicates will exactly express what you said out here. Okay. Now we're going to move into the execute clause. Remember in the example we saw earlier, there was a retire success at the end of the add and SLL, et cetera, instructions. So that's just a little enum, and enum is just as you think it is from C or C++. It's just tags that were constants that we're defining, but strongly type check. Unlike C or C++, where enums are just synonyms for integers, these are not integers. If you try to add one to one of these, you'd get a type checking error on this. But other than that, they play the same kind of role. And in this particular case, again, since there's only 2 values, technically we could have not defined a new type, just use bool wherever we needed this. But once again, from a strong type checking standpoint, it's good to, and readability standpoint, it's good to define things like this. So here's the execute clause for the LUI and AUI PC instructions. And so the fact that a function says I'm defining a function, the fact that I've said clause here tells the reader, or including the Sail compiler, that this is a clause of what I had said earlier that I would define in clauses. Here's the function I'm defining, execute, and it says this clause applies when this pattern matches. So essentially, if you tried to give any other kind of AST here, you would have pattern matching failure, and this clause would not apply. So if you think of all of these clauses as in a big if then else or a match statement, I'm defining one of the clauses. It just says this line does not apply. So you go on to the next one. So assuming it does apply, these variables in the parentheses give names to those fields that are associated with, that are in that data structure. That is that instruction. So the first line here is basically saying, let's first create the full xlen wide offset. And the way it's doing, so first of all, off by saying that it's this type, that's saying it's an bit 32, bit 64, depending on what xlen is. And here, this constant OXOOO, as I mentioned before, it's a literal constant, which Sail will take as a 12-bit value, a bit 12 value. It knows that im12 is a 20-bit value, so that concatenation will give you a 32-bit value. guaranteed. But we also put in an sign extend here because in RV64 case, you are supposed to sign extend that up to 64. It won't do anything in the 32-bit case, but it will sign extend it up as necessary in the RV64 case. Then here, what we're doing is we are computing the value based on the offset. If it's and so again, return the register value is xlen bits wide that we're going to write into the register. Again, we match on the op, and if it's LUI, it's just the offset itself, and if it's AUI PC, it's basically PC plus offset, right? So there's nothing more than that. This function here goes back to repeating what I said earlier about you'll see in various places functions where you might want to hook in something to do something else for instrumentation or some other formal method or something like that. But if you don't have any of that, this is effectively the PC itself. All it's doing is it's reading the PC, adding the offset. And once we have the value, this line, and here we are seeing that that overloaded use of X, it's assigning the value that you just computed into RD. And then the final value of the whole block is retire success, and therefore it's the value of the function itself. All right. Yeah, and again, strong typing makes sure that we've got all our bit widths exactly to right. This extension S knows how much it needs to extend, all based on the strong type checking and inference that we have. Okay, I think I've said all of this. Okay, the last, yes, sorry. Good question. The question was, how do you know it's a signed or unsigned edition? And so, yeah, so that's basically, where do I have it? Yeah, the question is, what is this plus? And in this case, based on the types and the overloading of plus, it'll get onto the correct plus. Later on, when we look at the next example, which will be on branches, there are separate branch instructions for signed comparisons and unsigned comparisons. You'll see I'll be using two different operators there. So it's implicit in, again, if you go back to the prelude, it's going to tell you exactly what plus means, and from the types and the type checking, we know exactly what it is. Okay, so in this place, one thing is the fact that off is a signed representation. I don't know exactly. The plus symbol is used to represent signed addition, and plus underscore U will probably be used if you were intending to do an unsigned. And the fact that you use plus by itself probably means signed. I don't know, Prashant, if you can confirm if that's. The question is, where is the information here that we're doing a signed addition? Sorry? The plus operator is going to presumably be used in places where we want to interpret xlen bits as a signed value. And if I was going to do an unsigned, I'd use plus underscore S underscore U or something like that, right? There'll be two separate operators like that. The fact that I've used plus, yes?
In my opinion, in this case, everything is unsigned because even S could be extended. Because actually, you have zeros on the right side, so it's the same.
No, both are unsigned. In fact, offset has been declared here as just xlen bits, which is just a bit vector, right? So this plus vector is not directly you think of as adding two integers. It's saying this plus is something I've defined earlier in my sale prelude or somewhere, which says, I'm going to give you two bit vectors. Please interpret them as signed bit vectors and add them. If I wanted to say, please interpret them as unsigned, instead of using this plus operator, I'd use a different operator, which is also defined in the prelude, which will say plus underscore U, for example. So you have to be very careful, absolutely, you have to be totally careful about that. And yeah, you'll have to sort of look at the prelude to see what does that plus actually mean. Somebody else had a question? I'm sorry, I can't.
You're extending the value up to 32 bits. You mean you get sign extended to 32 bits. So essentially,
Yeah. So I should make first a general comment, which I think covers all of these cases, which is that whenever you see these ISA specs, okay, when you look at an expression, let's say in C, and you see x plus y, your x and y will have some particular types. It could be an int, it could be a uint, for example, in x and y. And then there are rules in C which says, well, if you're doing two ints, plus means it's a signed addition. If you're doing two uints, plus means an unsigned addition. So there's a lot of stuff going on behind the scenes in that case. In the ISA case, well, first of all, these are not even ints. These are just bit vectors, right? And you're defining the symbol plus in this case to mean I'm going to give you two bit vectors. You don't even think of them integers yet. Inside the plus function that you interpret them as signed integers or unsigned integers. In this example, immediate 20 is a bit vector of size 20. And here where we did the, let's see, where did we do that? Where we did the extension S on line 2, we're saying, I'm giving you a 20-bit bit vector and a 12-bit bit vector, and please do whatever is necessary which concatenates into a 32-bit bit vector. Please produce for me the bit vector that is as if I'm interpreting this as a signed extension, right? So the type xlen bits is it's still a bit vector. It's either bits 32 or it's bits 64. So when you get to the plus line, both sides are bits 32 or bits 64, and the plus operator is defined as something that takes bits. Because I've used that particular symbol plus, please interpret it as a signed addition. Yes? You'll have to speak a little louder. So this is part of the plus operator semantics here, right? This is saying I'm going to give you two 32 or 64-bit as appropriate bit vectors, and you're going to do the plus, which is give me back the 32 or 64-bit vector as appropriate that interprets them as signed integers, right? So so everything about overflows and all of that is implicit in the fact that I chose that operator on these bit vectors. If you wanted to, you could define a different operator for that instead of plus. So like I said, there are very few built-in primitives. There is a big prelude that sets up all these operators up front, appropriate for the ISA. What are the things we're going to do in this ISA? So we choose operators that are convenient for us, and you can define any operator you like. You can do wrapping, you can do whatever you like on that. Okay, yes?
So the prelude, does the order of things as they come, is it significant that the prelude sort of comes before RISC-V thing? It looks like XS, for example.
Yeah.
The type of XS is dependent on XLEN.
Yeah.
So if I'm defining XS very early in the prelude, XLEN gets defined later.
Okay.
How does Sale deal with that?
So the question I'll just repeat the question is, what about the ordering in which we provide these definitions, right? I've shown you two different files. I don't know what order these files are processed in, et cetera. So I'll give you two possible answers. I'm not sure exactly what Sale does, but the first step is conceptually that we are just concatenating these files to produce one large text. There's the next question of, does the ordering in that logically concatenated file, does that matter? I don't exactly know the answer to that. It doesn't have to matter because I think there's enough information in the file that you could sort through these and put them in the right order, et cetera. But whether the compiler actually does that or not, I'm not quite sure. I don't know. Okay. So I mean, in my opinion, it's a tactical convenience on implementing the compiler. I have less work to do if I just assume you're going to give me things in the right order. But in principle, I could have written something that whatever order you gave it to me, because of the names and declarations, I could sort it beforehand and set it up right. I mean, you'll see a similar example in other languages also, right? If you look at in Haskell, for example, you write a Haskell program, the program figures out the dependencies and things like that. So it doesn't really matter what order you write those clauses. You could do a similar thing in Sail also. Okay. Last piece of for this LUI and AUI PC is the assembly mapping. And it's very similar to your encode, decode. It's just that your target, instead of being bit 32, is string in this case of text. And so what we're doing is we define a mapping here that says for these abstract names, LUI and AUI PC, what are the corresponding strings for that? And then we provide the clause in the scattered assembly mapping, which says when you have this type of a instruction, now what we're doing is we're using this caret symbol, which happens to be string concatenation. So on both sides, I should give strings, and it concatenates strings. So this piece here is getting the mnemonic for the op. This is just a constant for a space in your string. This is something defined elsewhere, which, given the register bit 5 register thing, it will give you a name for it, and that function can you can decide there whether you want to use the x1, x2, x3 notation, or you want to use the ABI notations for RA and SP and things like that. Separator is probably a space or a tab, and finally this is just giving you a string, which is the hexadecimal print of this immediate. In the code as it stands, you see there's a suffix because we have a different thing for different widths here. But again, that's something that Sail can sort out by itself. So I think there's an improvement in the works where this would be just through type checking, it'll figure out that you want the 20-bit version of this versus 11-bit version or something like that. So yeah, so in that one line, you have already explained completely the assembly to AST mapping of interest. So to take stock again, I'll probably say this again a little later, for each of these instructions, there's an AST union clause. So you're saying, what is the abstract decoded view of this opcode? You're specifying the encode decode mapping. How does 32 bits go into the abstract decode view and vice versa? You're specifying the execute function. Given the abstract view, what does it do? And you're specifying an assembly mapping, which says how do you go back and forth to strings. Yes? I don't, his question was, is that exactly one space, or exactly what is the parsing algorithm in some sense that I'm using? I don't know what the answer to that question. White space, so space is just a white space, I think. Yeah, in fact, that seems to be a harder problem to implement this mapping. Encode decode is straightforward, we understand what that's saying. This one, I don't know whether it's always decidable even, that you've written something sensible there. I mean, certainly going to the string part on from left to right is easy, but going from the string back, I could just imagine all kind of hairy things going on there. Yes?
In a real-world assembler, you typically can have a label or expression or operators as well. Is that model here as well, or do you require it to be an X value?
So yeah, I think, so this is just giving you a sample of what you could write. You can define many different encodings to strings. Different assembler conventions exist in different compilers and things like that. So there's no silver bullet there. This is just saying this is one mapping into strings. And you could write other functions, other mappings, etc. You could say the assembly 1, assembly 2, and each one of them could be a different way you map these things. In terms of the larger thing about how you put together the assembly program, including labels and positioning pieces and all, this is not taking any position. This is just saying for this instruction, what would the line look like? It's not doing anything about context around it. Okay, so let's zoom through. Oh, sorry, one more question. I think that's the question was, is the assembler mapping formally official in some sense? And I think the answer is no. In other words, even both in even the textual document, there's sort of a one rudimentary page at the back. People actually go grok what GCC does or LLVM does for this. I think that's still an unresolved question. So what I would like you to take away from the assembly mappings that you see here and in the sale code is just the notation of how you would say it. Don't take it as gospel. Yeah. Okay, we're going to go quickly through one more compute, in this case a control transfer, but not a memory thing, because I see we are 1.5 hours in, and we still have quite a lot to get through. So, but you'll see the pattern is exactly the same, right? So first of all, in the assembly type, branch type instructions, they're called B type, and typically funct3 tells you which of these kinds of branches it is. And then you have the register designators, and then here you have a 13-bit immediate. So that's the other interesting thing, if you haven't noticed this before in looking at this kind of code. The bit field in the instruction is only 12 bits, but it's assumed that it's 2-byte aligned, because whether you're working in compressed mode or in base instruction set mode, you should either be 2-byte or 4-byte aligned, so the least significant bit is always 0. So they're taking advantage of that here by saying that these 12 bits will actually be interpreted as bits 1 through 12 rather than 0 through 11. And you'll see that in the indexes. There's an index there which says 12, and you'll see there's no index there which says 0 out there. And that's explained in the text, normally in the spec. But this notation tells you how you put together that 13-bit immediate from there. So in the B type, we actually, as part of the decode, we do that 13-bitification of the 12-bit value. And that's why this component of the B type is 13 bits. You have your register specifies and the branch op, which is going to be one of these. Here's the encode decode mapping. This should be easy to read now. This is a local mapping that says how does the 3-bit funct3 field get encoded into an abstract BOP, and it just shows you all the different encodings we're doing out here. And then we use we add one more scattered clause. We already did the scattered clause for LUI and AUPC. This is adding now a scattered clause for all these branch instructions. And it's basically saying the encode is a B type with these fields, and these fields are this notation on the right is basically saying it's the bit concatenation of these things. So this is the major opcode for the branch instructions. The RS1, RS2 are fairly straightforward. Then the funct3 field is the encode decode version of the op. So remember, the op in the B type, that is this field, is one of these abstract things. So here we want a 3-bit field for funct3, and we get that by just applying this mapping to this abstract value. And then at various places here, we're just sort of picking out contiguous pieces of the immediate that are needed to assemble the overall mapping. So if you sort of just study all of this in detail, it's essentially expressing what's in these kinds of notations out here. Okay. Yes?
How fathers had in mind, doing so bizarre with sweeping from values?
Sorry?
What's
Can
the
we take that
reason?
offline? I'd love to tell you why. Let's do that afterwards.
Okay.
So you're asking why it's doing this funny kind of thing? Okay, I think that's probably, let's just take it as gospel. They've done it, and we have to follow that. Okay, all right. Here's the execute clause for the branch. It's basically saying when you, in this clause, matches instructions of this decoded type. The first two lines are just reading from registers using our X overloaded X notation. And then we're computing a Boolean value called taken. And that Boolean value, the right-hand side expression, is just a big match case statement on the 6 different ops. And then depending on what it is, you can see the actual comparison. Now here you're seeing something that relates to our discussion a little earlier about plus, whether it's signed or unsigned or not. So for example, BLT means bacon, lettuce, and tomato, but it also means branch less than. and BLTU means less than, but please interpret those bits in an unsigned way. So what you see is I'm just using 2 different operators here, which are presumably specified somewhere in the prelude. Both of them are getting exactly the same bit patterns on their left and right arguments. One of them interprets it as a signed value and does the right thing for that, and the other one interprets it as an unsigned thing. Okay, and then, okay, let's look at the execute clause. The execute clause, what I've shown you here is, you see I have dots here, which means up to this point we have decided whether the branch is taken or not, and we have also computed what the target will be if we take the branch. That is, it's the PC plus the sign extension of the immediate value, which is a new PC of length excellent bits, which is an excellent bits type. And then so now we proceed, so that dot here is the previous slide. So first of all, what you will see if you look at the code is if then else. If you're taken, we're going to do some things, otherwise retire success. If you're not taking it, then you're done. So we just retire success. So what happens if we are actually going to take it? So if we are going to take it, we have basically a check to see whether we are properly aligned. So basically, if you're in an RB32 setting, the bottom 2 bits need to be 0, and if you're in an RBC setting, only the bottom bit needs to be 0. So that's basically what this little bit of code is doing. It's saying if I'm not in RBC mode and bit 1 is set, then this is not correct. So aligned. So then we are going to call a function called handle memory exception. We're going to talk about that in a bit in more detail, but conceptually it's saying do whatever needs to be done to set up CSRs and all in order to take a trap. Get ready for that. In fact, do everything that's needed as part of the trap. And this instruction itself is not counted in the instruct thing, so we return a retire fail for this. Okay. And if it is aligned, then basically all we're doing is we're setting the next PC. Again, we're doing it through the function because we're doing hooks. We could have directly assigned it to that PC global variable as well and retiring success. Okay. This is the assembly mapping. I think let's skip this. It's nothing new or interesting over here. It's just the same pattern as you saw before. And just take a deep breath. Where we reached so far is you get the general pattern. That is, for any opcode that we're going to talk about, we have an enum. We add a clause to the AST to describe the decoded view of that instruction. Secondly, we take the encode decode mapping and we add whatever we need there to say what should we do for this instruction. We add a clause to the execute which says what the instruction actually does, and finally we do the assembly part as well. Okay, so for more example, we're going to be looking at a load instruction shortly, because so far we haven't looked at memory access yet. But we'll just focus on the execute. I think all the AST and the encode, decode, and the assembly part fairly boring. Okay, so let's go look at a load instruction. So this is basically the pattern in the enum for the pattern for the AST that we would have provided. That a load instruction has an immediate, it has an RS1 and RD. There are, whenever you're loading things that are less than the word length of the RV32 or RV64 that you're doing, there are two variants of that load. One which says when you bring in the smaller number of bits into the larger register, should you sign extend it or zero extend it? So this is telling you whether it's signed or unsigned. The width says, are you doing a byte load, a half word load, a word load, etc. And AQ and RL are about the acquire and release semantics, which are also there in the instruction. Okay, so let's take a look at how what I'm showing you is pieces that are inside the execute clause of the load instruction. Load and store instructions, because they're interacting with memory and they could involve virtual memory and things like that, a lot of things have to be done. It doesn't all fit on a slide, so I'm going to go piece by piece on this. So first of all, the offset is the sign extension of the immediate. And what this is doing, again, is conceptually just think of it as a no-op in general, but this is where you could add a hook which says, at this point you can sort of announce that I have the address that I need into some extra hooks or instrumentation, or in your concurrent memory model, you could be announcing the fact that you got an address. You can do all kinds of things within that function, but if you leave that aside, essentially just imagine that you come back saying, yes, this address is fine, and here's this address that you computed from the RS1 and offset is the virtual address itself. Okay, and if it wasn't, if there was some issue there, for example, I don't know whether it checks alignment or not over there, but you could handle a data check error there. And okay, then there's in fact here there's the misalignment, and it's, sorry, that's just repeating what I just said a moment ago. And if it succeeds, if it is in the alignment check, now this is, I should say, this is not taking any position on, because there is an implementation choice in RISC-V of whether you trap on misaligned addresses or whether you actually handle them in your hardware, for example. Your check misaligned would model that appropriately. It may return misaligned if it is misaligned, or it may not return misaligned. And so then the next thing we're going to do is we're going to do a translate address, and that's a little bit of an iceberg. You're going essentially, think of that as the TLB and the page table walk and everything that's going on, possible page table walks that are going on. And when you come back from the translate address, you come back with a failure. You can come back with a failure because in your page table lookups, your permissions may be wrong, you may be unmapped, you may be misaligned, all kinds of things can happen during your page table translation. So again, if you had a failure, you go into an exception. Otherwise, you'll succeed, and then what this is doing is it's branching on the size of the access that you're doing, and depending on that, it's calling process load appropriately with the number of bytes that you're trying to read. So process load is taking the saying, here's the virtual address and the actual address. Here's this is the data that we're going to read. Here I'm doing a memory read at this address with the acquire, release, etc. And then I'm going to process the load given its other information, in particular the RD. Where am I going to load it into? And yeah, so that's there's a fair amount of code there in dealing with loads and stores, going through virtual memory, exceptions, page table walks, etc. I've elided a lot of it, but it's at some level obvious. You're just enumerating all the kinds of things that have to be done during a load and store. You had a question?
I saw that we call the translate for Decode to convert it from virtual to physical.
Yeah.
But I didn't see a translate called when we computed
When you computed what?
when we computed the branch target with the branch instructions.
Yeah, there was an offset computation. The question was where was the address computation on the branch, and the answer is this line is adding PC plus immediate, and that's the branch target. No, the branch is done within the address space of wherever you're running. If it's physical, it's physical. If it's virtual, it's virtual. It's when you fetch that instruction that you will interpret that as a virtual or a physical during the fetch of that. The branch itself takes no position on that.
I saw the next slide and you use main target, but so there is maybe something.
Yeah, there are a lot of dots in my slides. Yes. Okay. Now we are 1 hour away from the end as this clock has started counting down. So, okay. So let's talk a little bit about our exceptions. So as you saw in that, both in the branch instruction where we had a misaligned target and also in the, I think we had a misaligned target. Certainly jump instructions can have misaligned targets. And also in the load instruction, you can have all kinds of exceptions. And we sort of punted it by saying we're calling some function to do that. Let's take a look at some of those details in a little more detail. So you'll see enums like this. This is describing all the different defined interrupt types. You could have more in an extension, but these are the baseline definitions. Here's a function that tells you what the encoding is for all of these things. I think this is probably the value that will go into the mcause register, should you actually get to that point. And then these are all the different synchronous traps. I think these are the external asynchronous exceptions that can happen, and these are the synchronous exceptions, which are all the ones you see here: address misalignments, illegal instructions, breakpoints, environment ecalls, and so on. Ecall, scall, and page faults, all of that. Okay. One quick sort of general observation, which is you'll see here that the external interrupts have just been written as an enum, whereas here the synchronous interrupts have been written as a union with tags, but all the unions, the information carried with them is unit, which is uninteresting. So why not write that as an enum as well? And as I understand it from Prashant, this is to accommodate certain extensions. So there's an extended version of RISC-V that the Cambridge group does called Cherry RISC, which involves further security features and so on. And they need to be able to carry additional information. So in that version of it, one of these unit things would have been changed to actually carry some information of some type. But modulo that, I think you could have done this as an enum as well. Okay, some other more definitions, a little nitty-gritty over here. The first box is actually not even sales specific. Any of you who have looked at ML or OCaml or SML will be familiar with this, or if you're a Haskeller, it's the same as the so-called maybe type in Haskell. Wherever you carry optional values, you think of it as a union. It's either something carrying something of type A, or it's nothing, in which case it's not carrying any information of any interest. And this we use in describing the information we want to carry with a synchronous exception. What is the exception type? For some exception types, you're going to carry optionally some XLEN bits of additional information with it. And this is for further extensions, you may want to carry even more information along with it. So we're using option types there. And then here's the handle mem exception function that we saw a few slides ago that we invoke, it's basically saying here's the address of interest that provoked that exception, and here's the additional information about that. And what we're doing is what we are calling is a more generic exception handler. So this handling of exceptions is layered through a couple of different layers, going from very specifically, I'm handling this specific kind of instruction. This gets funneled up to sort of a general exception handler. So where we've created some data for it, and we are passing it in here, this over T over here, along with the current privilege. And when you come back from this, what you will get is the program counter of your trap handler, where you're going to jump to in order to I think that's the case, right? Yeah, and that's what the set next PC is about. Here's the more general purpose exception handler. It's basically the privilege and this control result. And you can see that it basically has 4 clauses. One is the general thing for traps. And then the other kind of thing is the control for the returns from traps. And there are 3 different kinds of returns for whether you're returning from M, from machine, supervisor, or user privilege. And that's what these things are here for. Okay, I think in the interest of time, I should probably skip this. So this is the trap handler function. It's in the RISC-V syscontrol.sail. Del privilege is the delegated privilege. So if you've looked at the trap handling code and in trap handling specification for RISC-V, it's fairly complicated. There are many different kinds of traps. For different types of traps, you have to save away values in certain CSRs, like the empty valve, trap valve register, and the previous privilege, the previous this, a whole bunch of things you have to update in various registers. And there's also a concept of delegating trap handling. So by default, you have your 3 privilege levels, M, S, and U for machine, supervisor, and user level. In general, when you think of a trap, you think of it coming into the M level, but often those traps are relevant at the higher level itself. You can even handle some traps and interrupts right at the user level itself. And the way that works is the trap conceptually comes into the M level, but it then can be instantly delegated up to the supervisor level or further delegated up back to the user level. And so that's what the del prev is. It's about delegation. And so basically it's looking at the different causes and setting up all the right things for this. Yeah, this is a little messy, but exception handling is a little messy. So I think that finishes the section of the reading part of the tutorial where we're just looking at the instruction semantics itself. So far, I haven't said anything about executing programs. I'm just telling you what one instruction, what does this do? How does this instruction encode or decode or become assembly thing? So let's talk a little bit now about the next level up, which is how you actually execute sequences of instructions or programs. So this separation is very deliberate. And the reason is because you can package up this level in many ways with different kinds of next levels up on how you fetch and execute instructions. The simplest version, which is the default you'll get when you build in the SAIL repository, is a completely sequential fetch execute loop. So each one of these semantics that I've shown you, you can just think of executing programs as just a concatenator. You do the decode, execute, decode, execute, decode, execute. So the outer level loop is just going to do that. But that's just one choice of how you package up these semantics. If you're trying to model superscalarity, for example, you might have an outer level loop that is able to fetch 2 instructions at a time and invoke two copies of the semantics, one for this instruction, one for that instruction at the same time. You can model an outer level that involves pipelining, where you fetch an instruction and you start a thread to execute the semantics of that instruction. And before that thread is finished, fetch the next instruction and start its thread and so on. So these are all concerns of what you're trying to model. And you might wonder, aren't those all implementation details? Why are they visible at the semantic level at all? And the answer is really that very deliberately in all ISAs, including RISC-V, we do expose some of that messiness up into the actual visible semantics of the instructions. This is why we have fence.I, and sfence.va instructions. If you're always thinking of it purely sequentially, you never need those instructions. Hardware has to do it by some magic, but we deliberately expose it so that hardware is allowed to play these games, and so we need to model those kinds of concurrencies. And similarly, not just these fence instructions, but the other place where implementation, what you might think of as implementation artifacts, creep up into the semantics is on weak memory models. Because if your semantics cannot model the idea of reordering, et cetera, you're never going to be able to catch certain things that might actually happen in your implementation. So there's a deliberate separation of, let's separately talk about what an instruction does, and let's separately talk about how we package that up into fetch and execute kind of packagings. Okay, so what I'm showing you is just the sketch of the simple sequential fetch execute loop. And this is when you do a make in the directory, that's what you're going to get. So appropriately, there's a file called main.sale, which is the top level main. And all it's doing is the first two lines are showing some initialization of the program counter and the model itself. And for example, the initialization of the model might set up the initial value of the M status register and the trap vectors and whatever, something to get started. And then we call this function called loop, which is sketched in the next box down here. And the loop, as you can imagine, is just a loop. It just repeatedly does something. It calls step over and over again. And the arguments and results are not important for step in any semantic sense. When we build the simulator out of this and we run it, it's good to have things like instruction traces and so on. We want to know this is instruction number 35, this is instruction number 36, et cetera. So we have instrumentation like step number and things like that. But conceptually, all that's happening in that loop is just a call to step. And then here's the step function itself. And what you see is that it's the top. So we're going to do something which returns either a success, the instruction either retired or not. This is where the retire success, retire fail shows up, and a Boolean, whether we did a step or not. And if you look at the right-hand side of that binding, the first thing we do is to call dispatch interrupt at current privilege. So this is the place, conceptually, you can think of interrupts as happening between instructions at some unknown place. So this is checking whether an interrupt is pending. And specifically, what's going to happen here is in the RISC-V context, if you look at the MIE and MIP CSRs, the machine interrupt enable, the machine interrupt pending registers, it'll be looking at those registers to decide, should I handle an interrupt at this point or not? And then, so if there is an interrupt to be handled, it's calling this function that does it. And it is returning retire fail. So I didn't retire an instruction to do this. And I didn't take a step either. And if there's no interrupt pending, then what you see here is that I'm going to fetch an instruction by calling this fetch function. There's a hook by which you can instrument it if you like. And the fetch result will tell me whether I've got a RVC instruction or a 32-bit instruction. So this match dispatches on that. And then if you look at the base, you decode what you got from the fetch to get an AST. You set up what your next PC by default would be, and then you call the execute function, which using the pattern matching that we talked about earlier will pick the right clause depending on what kind of instruction it is. And similarly, you're seeing this for the compressed as well. So I think that, yes? That's a good question. I'm not quite sure. The question is, why doesn't the compressed clause have a next PC setup? I think there is a little bit of a stylistic question whether you should even say anything about next PC here or just think of it as part of the instruction semantics. I think maybe it's not consistently done in this case. Sorry? Yeah, I'm saying in both cases it could have been done in the instruction or it could be done outside. It seems to have been done one way in one and not. Oh, it's in the code, and my Emacs skills got rid of it. Okay, all right. Actually, that's a good segue into the next slide. First of all, that ends the reading part. We're going to go into the execution part, and we'll look at that in a second. But just to take stock of where we are, SAIL, to repeat almost what I said earlier, much earlier at the start of the talk, it's at some level just another programming language, right? Whether it's Python, C, Haskell, whatever you like, it's just another programming language. It's a formal notation with a semantics of what it means to execute SAIL. And, but it's been designed with features in it that help in one line talk about decodes and encodes and assembly syntax and things like that. It's heavily oriented to talking about bit vectors and doing strong type checking on bit vector sizes and so on. And it's very simple and clean in the sense that it uses very few combining forms. And these are all pluses from the point of view of clarity and precision, which are essential for any kind of formal spec. So in principle, if you wrote an ISS in C or you think of Spike in C++, these are all formal specs in a certain sense, but they may not be as suitable from the point of view of making sure you got it right. In other words, do you implement the spec could be, you could have had a bug in writing a C++ code in Spike, for example, and you could do that here too. You could have a bug in this, for example, missing PC +2 or whatever that I had over here. So at some abstract level, you're going through the same debugging and convergence process to make sure we've got it right in this spec. And the more eyeballs that look at it, ultimately the buck stops at eyeballs. That is, people have to look at this and identify if we've got it all right or not, and we come to a consensus that this is what it is. And the choice of this language is precisely because of precision in clarity, simplicity in the semantics, and we know how to connect. When you have a language like that, we know how to connect it to other formal tools and use it meaningfully in those kinds of things. Yeah. Okay, so the question was, there are several formal models out there. There were 6 pursued within our group itself, and there are more being pursued outside the group by other eyes. What made us choose the SAIL model? And it is basically a combination of readability and maturity and completeness. So and I actually talked about this on Monday in my talk or my status report, but basically, of the 6 that we pursued, none of them can claim anything close to the fact that SAIL has been used in anger, right? It's done the whole of ARMv8, so that's a good benchmark, and PowerPC and all that. So it's a good confidence builder that it's capable of handling things at scale. And from a readability standpoint, the fact that it's a DSL purposely designed for ISE spec, I think it also wins on that front. I think if you look at all of the others, and then if you look at semantic completeness, I think 3 or 4 of them reached similar RV32 GC, RV64 GC completeness. But except for SAIL, nobody had actually done anything with concurrency. Everybody had plans in their head about how you would take the my for-risk model, or MIT's PLV model, or the GRIF model. Everybody has ideas that they can sketch out on a whiteboard how they would do concurrency, but it hasn't actually been done. SAIL has gone much farther than this, and it's integrated the virtual memory model. So I think from many of those dimensions, SAIL was the obvious choice. And we also did a public review. We got external feedback. We didn't get too much external feedback, but anybody we talked to, the consensus was clearly it's the easiest one to read, it's the most complete, etc. Yeah. Okay, so if you go to you don't expect to read any text on this. You can get a mental image of the shape of the picture. This picture is on the SAIL RISC-V website, and it was created by Prashant. It gives a little more detailed navigation of the dependencies. What are the different files in that model directory, and which files need what, and that kind of stuff. Okay, let's move into executing ISA specs. We have 40 minutes left. Okay, so this is where I'm going to just demo it. If you have it already installed, some of you I think have successfully managed that. You can also try it along as you go along. So what you will see in my tutorial GitHub repository is slides installation.pdf, which goes into great detail on what all you have to implement for execution. So this is what is referred to on this slide as step B, and also in those other slides. SAIL is built on top of another programming language called OCaml, which in turn has its roots in the ML, SML functional programming community. And OCaml is essentially designed and built and maintained by people in France. It's a pretty widely used industrial strength functional programming language. It's used in many companies for all kinds of purposes, financial markets, web services, all kinds of stuff. So it's really a very robust, strong, well maintained, efficient programming language, OCaml. So within the OCaml ecosystem, OPAM, which is mentioned on the slide, is the package manager for OCaml. So it's the bootstrap from which you do all this installation. The first thing you do is just install OPAM. And once you have that, using OPAM, you install OCaml, and using OPAM, you install, and OCaml, you install SAIL. And it all, in my experience, this all worked fairly smoothly. Now, the instructions in my slide, by the way, are all for Linux, Debian, and Ubuntu Linux. And of course, there's widespread interest in Apple process. I don't know exactly what it is yet, but we're working on that, and we might even be able to build a Docker image that you can just download and build. When that happens, I'll add it to this material. Okay, so when you go through that whole process, what you will see is these two files that you see right at the bottom of the screen, which are in the SAIL group's vocabulary. They call it an emulator. I've always used the word simulator for this, but you can read it either way you like. It's basically a standard ELF binary that runs on your x86 laptop or your workstation that has been compiled from the SAIL code that we've been seeing all this time. And as I said earlier, right now you build it either for 32 or 64, so you get two simulators like you see out here. And the other thing you will find in the SAIL-RISC-V repository is a bunch of pre-built ELF files and .elf and .dump files for all the so-called standard ISA tests. I believe there are something like 229 ISA tests, which each is an assembly language program that is focused on either a single opcode or a small group of opcodes, like the branch opcodes, for example. It's a small assembly language program which you compile and run, and you can run it through your test. It has a kind of a self-testing mechanism which prints out success or failure at the end of it, what it does. So what I'm showing you here is just, and this is just a partial listing of the 229. Marnie. Well, the other slide deck, the install slide deck, which is not this, there are two PDFs in my tutorial repository called slides installation.pdf and slides tutorial. What we're looking at is slides tutorial.pdf. If you look at the other PDF, it goes into lots of detail, exactly what directories to build, exactly how to keep clone, what make commands you should have. For Linux, it has chapter and verse on that. Okay, so this is just a small sampling of the 229-ish tests that you have, and once you build it, you can actually run it. So let me actually demo that. I'll go here into Sale RISC-V, and so let me first of all, so so first of all, let me just look at, show you the directory structure. So all the source files we were looking at so far are in this model directory, and all the tests are in this directory. So if you do an ls test, RISC-V tests, whoops. Here's all the elf and dump files that are pre-built for you. You can recompile them if you like, but they're already compiled for you. And then what happens is when you go through the build process, when you got everything installed and you say make csim for C-based simulator, the build process will use the Sail compiler to take the Sail source code. It compiles C out of it, and then it uses a C compiler to compile that. And what you finally get out of that in this directory, C emulator, is the specific things of interest are this executable and this executable. And once you have those executables, you can then run a test like, which I will just copy and paste from here. So I'm running the C-based emulator, and I'm running it on this particular ELF. All right, so if I run that, let me just pipe it through. That doesn't seem to work well. Let me just run it. I have the log for this, so you'll see a whole bunch of stuff coming through here. And let me just, I've pre-built the log for this, so let me just go in and show you that log. So the thing that zoomed by the screen is what I'm showing you on the Emacs buffer at the left. And this is just a trace of some interesting information during the execution. Here it's telling you the ELF file I'm running. It tells you the entry point at which the code starts. It tells you some initial CSR status. And then the things particularly of interest are lines like this one. So this one says, okay, this is instruction number 0. I'm running in M privilege mode. My PC is 1000, which is where there's a little bit of bootstrap code. And the instruction there is 000297. That's the 32-bit instruction. And the assembly listing is AUI PC T0, 0. And then here you see down here the instruction number 1, and then down here instruction number 2, etc. So if you follow those lines, you'll see exactly the instruction trace going all the way through the execution. And right here at instruction number 477, I'm finished, and I finally hit the success message. So these tests are originally written at Berkeley by the Berkeley folks, and they have a particular protocol on how they signal that they're finished, and when they're finished, did they succeed or fail? And so these tests, the simulator is set up to be able to reproduce that exactly, and you're seeing the outputs from that. Okay, and the other example, I'll just show you that log rather than running it. In fact, why don't I run that as well? I'll do oh, actually, I did run that one. So this, yeah, so I'm sorry, I think I showed you a different log first. I showed you the log for the RV64 running on the add test in physical memory mode. This one is for RV32 running the RV32UM, that's integer multiply divide. The U means you're running at user privilege, M, the whole test is at user privilege, M means integer multiply, V means with virtual memory, and specifically the instruction we're testing is the mul HSU, which says unsigned, signed versus unsigned, and when you do the multiplication, I want the upper bits, not the lower bits of the multiplication. And this one you'll see ends at 20,000 instructions, whereas the previous log I showed you had only 477, and that's because of the physical memory versus virtual memory. There's a lot of preamble to the test itself to set up a small page table and all that beforehand, and then the test itself is actually exactly the same as in the other case, except that all the memory references now will be going through the virtual memory translation. Okay, so that's basically about running standard ISA tests. So this slide is just showing an excerpt of what I just showed you on that log. Okay. I should also say that when you make, what I've shown you is just the C-based emulator, C emulator, but the SAIL compiler has many different backends by which you can produce an OCaml emulator if you like. You can also produce connections into tools like Coq and Isabelle and Hall4 and things like that. Okay, one other execution example I'm going to show you is the compliance tests. So you can think of the ISA test, I think of the ISA test at least as a placeholder until we have compliance tests that are more complete. So there's a compliance working group that's chaired by Alan Baum right here. Maybe you could raise your hand. And they're chartered with coming up with a compliance suite for RISC-V, and there's already a couple of releases of that for RV32i, I think, and maybe a few other things. But the way those compliance tests work is, again, anytime you have a test, you need to have some protocol by which you figure out, did it succeed or not? What do you mean by succeed or not? And how do you measure that when you actually run the program? And in the compliance suite, basically, what the compliance tests do is, in the process of running the test, and by the time you finish the test, it's set up a certain region of memory called a signature, which has to have an exact particular value for the test to be regarded as completed successfully. So conceptually, to check whether you're compliant on that test, you run that test and you check that signature against a golden reference model. So you could run it on your implementation, and you run it on the compliance test, and you check that the signatures match. So that's basically what this is. So, so first of all, the link right at the top points at the compliance group's working repository, which is RISC-V compliance under the RISC-V organization. And then there's a bunch of setups that you need to do to set it up. So why don't I just jump to showing you this stuff in a demo. So roughly speaking, this is what we need to set up in order to run the compliance suite using the SAIL model. So first thing you have to do is something that is actually true for any model you run the compliance suite on, which is point it at your RISC-V GCC compiler, your tool chain, because the compliance suite first compiles the test based on the particular architecture and choices that you made, and then it runs that test both on your model. And the second thing we do here through these is to set up, to point at where your SAIL RISC-V executables are, the simulator that we just built from SAIL. So you can once you do that, what you will see is that make sure that you have your GCC and your SAILs. In fact, why don't we do this? We'll go to the compliance. So where I am now is in the RISC-V compliance, a clone of the RISC-V compliance directory. And if I source let's widen this a bit. What you will see is that my path is set up right now so that I'm pointing at the RISC-V GCC compiler here, and I'm also pointing at the SAIL RV32 emulators and the SAIL RV64 emulators. And once you're done with that, you can run essentially on all relevant variants. So let me go here. So I'm running, the make file takes a target which says which is the simulator or execution engine you're using. And all variants is just what are all the different variants of the tests you want to run. And in this case, we're running, since we do full RV32 and 64GC, it's doing all the variants. And I'll just click on this, but we'll take a look at the log in a second. So it's just zooming through all the tests out here. And like I said, I think there are of the order of several hundred or something that you can get through. Let me look at SAIL. This is the log. So just a few lines, we look at it. Roughly speaking, what you will see is that, like in this line over here, you can see the leftmost thing you're doing is you're calling GCC. It's calling GCC on that. And then on the next line after that, what you're seeing is that it's calling the SAIL RV32 C-based simulator on the compiled ELF file. And then if you, after it runs all of these classifications of tests, you'll see that it does a bunch of comparisons. So each of these, it's produced that signature that comes at the end of the test, that can be dumped at the end of the test. And then there's some place in the compliance suite where a standard expected answers are given, and it's just comparing with that and checking, okay. So it's going through, it's showing you here that it's passed all of these. Okay, again, this is something you should try on your own. It's described in a fair amount of detail in these slides. Okay, the last, we now have 20 minutes left, so let me spend a little bit of time on extensions and what it takes to add extensions. You already have a sense of this from what we've seen so far. That is, you're going to extend the AST type to include the new instructions that you're defining in your extension. You're going to extend the encodec, encode decode function, to describe how those new instructions in their 16 or 32-bit form become these decoded instructions. That is how they become ASTs. Then you're going to define a new clause for the execute, which says, given one of these instructions, what it does. And then The assembly stuff is if you also want to get into that, but you don't really need to do the assembly thing if you're not doing any assembly language directly. So yeah, so that's basically what I've said here. Let me just show you a small case study, because I actually went through this exercise in October to add the F and D instructions. We're not going to go through all of those instructions. There are a lot of them. I just want to give you the style of how it gets done. Okay. In fact, you won't, when you just clone the repository, you'll be in the default master branch. You won't see it there. So what this slide is saying is there is another branch which happens to have my name on it at the moment, but it'll be merged into the master at some point. But right now it's a separate branch. If you check out that branch, you will see the code that I'm about to show you. So first thing is what you, and some of the things I'm showing you may or may not be necessary for your extension. All right. So the first thing we have here is that we are defining two files called flen-f and flen-d. So remember, we had a file right at the beginning of the tutorial where we talked about defining xlen. That's the integer width. So similarly, you might have a different width for your extension. In this case, we do the flen, and so these files are used for that. And if you're only supporting the f extension, then flen is 32. If you're doing f and d together, then the flen is 64. So analogously, we're just setting that up over there. The next thing is your extension may or may not define new registers. Floating point, we do. We have a floating point register file. So just like the integer registers, we define here the types in the f registers and then the f register file itself. And then your extension may or may not define new CSRs. And what this is showing is that we set up in the floating point, there are 3 CSRs that we add, which are set up in this fdx control.sail. So, and then finally, once we've set up all the state and the registers and all those definitions, if you look at these two particular files, fx.sail, fx, and instdx, they follow exactly the same pattern. They have an AST definition for each of the opcodes, an encode, decode, a execute, and an assembly. And so once you've done those files, now to build it, you need to tell the make process how to use the files that you've just, and to include the new files. So for example, if you look at the top level make file, you'll see lines like this. So you see the plus, this is a git diff that I've done here from the 2 branches, and what you're actually from the top of the branch and an earlier version that didn't have f and d. So what you see I've added, we've added some things that describe the flen, include the flen, appropriate flen thing. Then there is a line on default instructions. So what you see here is the fxed or the instdxed. And since D always implies F also, so this one is only in the case where you're doing an RV64. One other file you'll see here in this thing is again an artifact of the floating point. It may not be relevant for other extensions. In the floating point setup right now, we're not modeling the actual detailed floating point arithmetic, IEEE floating point arithmetic that's at the heart of the floating point. What we do in Sail is everything around that. So when you fetch instruction, how do you decode it into floating point instructions? After you've decoded, how do you read the floating point register file and get everything ready? And then you call this magic function, which says, do the arithmetic for me, please. And then at the outside of that arithmetic function, you get the results. And then you have to process those results. Things have to go back into a floating point register file. You might have to update CSRs in the floating point. And you might have to change the dirty bits in the M status that says that the floating point state has changed. So there's a bunch of other things. So all those Sail specific things, RISC-V specific things are all written in Sail. just that magic function we call out to Berkeley soft float, and just do the arithmetic inside Berkeley soft float. So that's specific to floating point. Your extension may not need any such call out to something outside. So that's basically it. And I think we're actually doing well. We have 15 minutes left. And so I think I should be able to get through the last few pieces out here. So just to recap, we've spent a bunch of time going through just reading literacy, how to read SAIL code. Yes?
So because you link to the executables on Berkeley, right, the soft float, that means that the formal spec relies on the correctness of that soft float type.
Correct. So the question is, doesn't the formal correctness rely on correctness of Berkeley soft float? And the answer is absolutely yes. So until we model the arithmetic itself in SAIL, that's going to be the case. But I don't think it's a high priority to think of that as a problem at the moment, because Berkeley soft float has been beaten by so many people over so many years, and number one. And secondly, I think most of the issues for implementation, certainly somebody implementing a CPU with floating point, they have to worry about what's going on in the arithmetic. But for most of the other purposes, I think it'll be fine. By the way, Spike also calls Berkeley soft float. Yes, another question? How will we get what? Extensions. So, okay, that's a good question. How will extensions get into this is, I think, your question. What's the logistics of that? That is actually a little bit TBD as to who owns it, right? So there is one proposal out there that the technical group that is producing the extension is responsible for writing the formal spec for it as well. It's analogous to another proposal out there also that group should also write the compliance suite for that extension. So these are two things that need to come with any extension, the compliance suite and the formal model. And it's not yet quite clear who owns the job of doing that. But yes, and there is going to be a so-called standing committee in the RISC-V Foundation called the ISA Standing Committee. Ultimately, they own it, but they may spin off a group to do this, or to add the extension, or to ask the existing TG that's producing the extension to do it. Anyway, there's something has to be worked out there. It's a little early to know exactly what the answer to that question is. Okay, so I think just a little bit more about SAIL, which is that, as this I've mentioned this before. This Popple paper is the definitive reference at the moment for SAIL, and these are all the players who have contributed to inventing and developing and implementing SAIL. I believe Peter Sewell being the head of the group at the University of Cambridge that does this, and I learned recently that Catherine Gray was one of the early creators of SAIL, and she's the one who picked the name SAIL, and actually she didn't pick it. She asked her mother, and her mother picked the name SAIL. And it's not an acronym, it's just a name that she thought was nice. So that's why we don't capitalize SAIL in any of this. It's just a word, not an acronym. Okay, so if you go to the SAIL repository, whose link I've shown here, what you will see is above SAIL, that is, things coded in SAIL include all those things in those sort of pink reddish boxes. There's a full ARM v8 spec, and by the way, that ARM v8 spec was not hand-coded. It was automatically translated from ARM's internal formal spec for ARM v8 into SAIL, but it's been heavily validated to ensure that it actually says the same thing. There's RISC-V, there's MIPS, there's Cherry MIPS, which is security extensions on top of MIPS, and there's pieces of x86 and PowerPC and so on. Underneath SAIL, in the other direction, what you see here is that of the three yellow boxes on the left, we just ran the so-called sequential C emulator. But there's also an OCaml emulator you can build. There's some work, I think, at Edinburgh that's doing automatic test generation from the sales spec. And then going on to the more formal tool side, it goes on to, there's the system, you have backends that will take it through Coq, Isabelle, Hall 4. And then through LEM, you can also interact with another very interesting and important tool called RMEM. And this tool is about modeling weak memory ordering systems and modeling them precisely. So, and there's a bunch of tools around that, like litmus test generators and so on. So there's a lot. What we have seen today is we've seen a few lines of code from the RISC-V spec, and we ran it through this to the sequential generator. So we just saw a small slice of this world today. So the last important topic I want to talk about is about concurrency. I mentioned this a little bit at the start of the hour, which is that instruction specifications for any ISA deliberately make visible certain artifacts that to first order you might think are implementation artifacts, but if you didn't do that, it would be very difficult to implement things efficiently. Specifically, things about out of order, weak memory models, and so on. And the idea that you might have separate IND channels for instructions and data, and therefore there's a coherence issue between those two. So that's why we have a fence.i instruction. You're likely to have caches, and so there's a coherence issue between what your heart sees and I/O devices see. So that's why we have a fence instruction. You're likely to use translation look-aside buffers for virtual memory translation. So there's a coherence issue between what you write when you update a page table and when you start translating using that page table through the TLBs. That's why we have the sfence.bma instruction. And then finally, whenever you have a multi-heart thing, you're all talking to memory, things, you might do things out of order, etc. What does all that mean? So ISA is deliberately, in order to not rule out efficient implementations, make these things visible in that abstracted sense of fence instructions in WMA. So you can think of what we've seen so far as one of these blue boxes, right? For each instruction, there's a blue box which says, here's what it takes to execute this particular instruction. And we also saw a little bit about that we mentioned that there's a fetch function, which is another, we saw the load function, but there's an analogous fetch function that fetches an instruction. So you can think of a sequential wrapper around the semantics as just a loop that goes fetch and decode, execute, fetch and decode, execute, like that, right? And nothing interesting happens. But you can also, to foresee what's going to happen next, you can think of each of those executions as a little thread that's saying, what is this instruction doing? And during that thread, there are certain sort of lifetime events of interest. Oh, I'm going to be reading a register here. I'm going to be writing a register here. If it's a memory access, you say, oh, at this point, I know what my effective address is. Now, why is that interesting? Well, once you get to concurrent models, just think of the effective address announcement, that it's now ready. If you have an out-of-order processor that's competing loads and stores, you know you have a store instruction. You don't yet know what value you're going to store, but you got the effective address. The moment you have that, you can say, this other load is looking at a different address, so I can allow him to go ahead of me. So these kinds of announcements and events allow you to manage concurrency. So what you see in the RMEM system, which I showed on that slide a little earlier, is a different packaging of the same semantics that we use for the sequential interpretation. And it actually, in the red box that surrounds it, it has a model of memory, including managing weak memory orderings. So you can think of the things coming out of these boxes are little announcements. I want to load. Here's a memory request, etc. And things coming back into the boxes are responses from memory. Even registers. So for example, if you want to allow out-of-orderness that comes because of register renaming, even a register read becomes a request. I'd like register R5, and please tell me what the value is from R5. And you may have to go through a renaming mechanism to get the value out there. So the RMEM system, just very briefly at a very top 10,000 foot level, is It's a different packaging of the same semantics that is allowing you to launch multiple instructions either even from a single heart due to pipelining, superscalarity, out of orderness, or due to multiple hearts, you can launch multiple instructions at the same time. And these things are conceptually sending and receiving messages to the RMM environment saying, I want to read this location in memory, I want to write that location in memory, etc. Or I have this address available at this point, I want to read such and such register. And the box outside manages the access to that. So if you think of these events as ultimately being ordered by a graph of what order things should happen in, and the semantics of the language and the weak memory model tells you what are the constraints on the graph, that red box is managing that graph. It's incrementally and dynamically building and managing that graph. So in fact, the separate group that was run by Dan Lustig and finished off last year actually on defining the weak memory model, they actually came up with 3 or 4 different formal specifications. I think most of them were so-called axiomatic specs of the weak memory model. Axiomatic specs are a way of just writing properties, which are fine if you want to check, but it's not that easy to figure out how to execute something with that. They're okay as a checker, just like in, say, system Verilog, when you write assertions, they're fine as checkers, but you might ask, if I wrote that assertion of the property, why do I have to write my system Verilog design? Can't you derive it from that? That's a much harder problem. So similarly, axiomatic specs exist for the weak memory model, but one of them is an operational model, meaning that it's written in this style of where it's clear what it means to execute that in a process, etc. And that model is written with the RMM system. So this integration between the instruction semantics and the weak memory model in RISC-V already exists because of that connection. And one last slide. I think we can probably skip this. We've talked about this briefly already. One question was, why did we choose SAIL? I think I addressed that question. We had a group we ran for about 2 years, very nice weekly meetings. So right now, it's basically done. The rest is just sort of logistics on cleaning up, polishing, improving this tutorial, getting documentation added, etc. And the other thing is, because all the repositories I'm pointing to are active research projects, we want to isolate from the churn that might go on from those repositories. So we'll have a process to snapshot it into riscv.org.
What happens for things that the current spec gives you an option? If you want to get a number, you mentioned the example of analog.
Yeah.
Is that software proposed and we have
Yeah.
both options?
Yeah. So good question. So the question to repeat is, there are many implementation options that you will see in various sentences throughout the textual specs. You can trap or not trap on misaligned. You can choose to implement this counter or not. If you implement any PMP, you should implement all PMPs, things like that. And if you implement the SV39 virtual memory scheme, you must be implementing supervisor mode. There's lots of choices and constraints on meaningful combinations of choices as well. So this has been well recognized now, and to date, the work that's happened is primarily in Alan's group on compliance, because you have the same problem. When I'm running any one of these simulators, I want to configure it to have the specific choices that an implementation might take. And so they've, between them and IIT Madras, the compliance group and people at IIT Madras, they have a system which is based on a YAML file declarative way of specifying a lot of these things. And you can think of that YAML file as another parameter that goes into either running the simulator or building the simulator or both, so that you can set up the simulator to behave exactly like you want it to behave, like a particular implementation that you're comparing it with. Typically, implementations make specific choices and they hardwire it into the design. These things need to be a little more general purpose, so you can configure it to match those specific things.
Let's have a question about maybe about implementation. Is there a path forward to take
cycle accurate simulator, with perhaps delays or cycle counts of instruction execution times, bench times, just trying to get closer to implementation derived from a SAIL model.
So I'll give you two answers to that. I think one first of all, the point of these specs is to deliberately not say anything about cycles. There are properties like in wait for interrupt, progress guarantees, or when you're doing load reserved store control, store conditional progress guarantees. So there is a notion of time a little bit in a very abstract sense, but not at the level of cycles or anything like that. And if anything is measured in time, it's how many instructions, an instruction count, and nothing more than that. Now, one dimension of where you're going is there are certainly groups, including MIT's group, where they're trying to design CPUs correct by construction by systematically transforming a formal spec one step at a time, where every step has been proved correct. I'm adding a pipeline stage, I'm adding bypassing, I'm adding branch prediction, et cetera. And every stage you prove it correct so that you don't have to, at the end, prove your implementation correct. It's correct because of the chain of proofs that you already have, that every step was it. So that's one dimension on which what you're saying happens. The other dimension I want to say is that if you look at things like QEMU, QEMU, et cetera, right? Those are also, and I forget what the one is that everybody in the ISCA community uses. There's a, GEM, the GEM simulator. These are also claimed to be cycle accurate, but cycle accurate with respect to what, right? So they have a slightly looser, less precise meaning of cycle accurate, where they model cycle latencies, right, in a certain sense. They're not modeling any specific microarchitecture. They're saying, let me assume that this thing is going to take so many cycles. Let me assume that takes so many cycles. And if I make those assumptions, when I run this program, what stalls do I have? What pipeline bubbles do I have, et cetera? That's a different dimension, which certainly somebody could take this and move it in that direction as well. Yes?
Very practical question. If I have an internal C functional simulator, and for legacy infrastructure reasons, I need those Decode execute data structures in a specific way. Do you see anything unreasonable or untenable by modifying, let's say, C backend?
No. So yeah, the question was, if I have a legacy ISS, for example, I've already written things, maybe it has extensions, it has valuable stuff that I need. The question is, can I use any of that in the simulator? Absolutely. The thing is, already one example I gave you where we are calling out to C code is in the Berkeley soft float when implementing the floating point, right? So similarly, in the decode function, you could call your magic function, which calls out to C, and then you can call your function. You just got to, there's a standard protocol and mechanism by which from SAIL, you can go into C and come back. You have to, it's the usual foreign function interface question. What are the representations of data and things like that? Provided you design those all carefully, you could integrate it certainly with this. Yes, sorry, this just 1 minute. Yeah, okay, we are 3 minutes over time, so we'll take it offline. Okay, well, let me finish with by saying thank you, and you can hopefully, this tutorial we hope for you starts a more pleasant journey. Thank you.